Good morning, everyone. I'm Dr. Sandip Kumar Park, and I'm excited to welcome you to today's presentation. Today, we'll be exploring the fascinating world of fluid mechanics. This is the first slide, so I want to give you a quick overview of what's ahead. We'll cover the fundamental principles, some key applications, and important concepts in fluid mechanics. I hope you find it engaging and informative. Let's get started. Welcome to our discussion on fluid mechanics. Aquatic exercises have proven to be incredibly effective in rehabilitation for a diverse range of patient populations. This includes children, orthopedic patients, those with neurological conditions, and individuals with cardiopulmonary issues. The unique properties of water, such as buoyancy and resistance, make it an ideal environment for therapeutic activities. Physiotherapists play a crucial role here. They help patients maintain and improve joint mobility and muscle function through various interventions. These include exercises tailored to individual needs, hydrotherapy sessions, relaxation techniques, and other specialized treatments. Overall, integrating aquatic therapy into rehabilitation programs can enhance recovery outcomes, making the process more comfortable and effective for patients. It's a perfect example of how understanding fluid mechanics can directly benefit patient care. Let's delve into fluid mechanics, which is fundamental to understanding aquatic exercises. Essentially, it's the study of how fluids behave when they are at rest or in motion. This knowledge helps us optimize therapeutic interventions in water-based therapy. When we talk about fluid mechanics, two key areas come into play: hydrostatics and hydrodynamics. Hydrostatics deals with fluids at rest. Think about how water supports objects or the buoyant forces involved. Hydrodynamics, on the other hand, focuses on fluids in motion, like how water resistance affects movement or how currents influence exercise. Understanding these concepts allows us to tailor aquatic therapy sessions more effectively, ensuring we utilize the properties of water to support stretching, strengthening, joint mobilization, balance, gait training, and endurance exercises. So, fluid mechanics isn't just a theoretical concept. It's a practical tool that enhances the safety and effectiveness of aquatic interventions. Let's talk about fluid mechanics, and more specifically, hydrostatics. Hydrostatics is a fascinating branch because it focuses on fluids that are at rest. When we say at rest, we mean that the fluid isn't moving. It's still, which might seem simple but actually involves some complex concepts. In hydrostatics, we're primarily interested in the pressure within the fluid. This pressure isn't just a random force. It's exerted equally in all directions at a given point in the fluid. Understanding this pressure is crucial because it affects everything from the design of dams and submarines to how we measure blood pressure in medicine. So, the core idea here is that hydrostatics helps us understand how fluids behave when they are not in motion, and how the pressure acts on immersed objects. This understanding is fundamental because it connects to many practical applications and sets the stage for more dynamic fluid behaviors we'll explore later. Remember, when dealing with fluids at rest, the key concepts are equilibrium and pressure distribution, which are essential for analyzing many real-world engineering problems. Today, we're focusing on fluid mechanics, specifically hydrodynamics, which is all about fluids that are in motion. When we talk about hydrodynamics, we're examining how liquids and gases behave when they flow, how they interact with their surroundings, and what factors influence their movement. This area is crucial because understanding the dynamics of moving fluids helps us design better ships, airplanes, pipelines, and even understand natural phenomena like ocean currents and weather patterns. Essentially, hydrodynamics connects deeply with the overall theme of fluid mechanics by highlighting the behavior of fluids in motion, which is fundamental to many engineering and environmental applications. So, as we proceed, keep in mind how these principles underpin much of the technology and natural processes we encounter every day. Let's take a closer look at fluid mechanics, specifically the concept of buoyant force. When a body is immersed in a fluid, whether it's just partially submerged or completely underwater, it experiences an upward force. This is what we call the buoyant force. Now, an important point to remember is that this force isn't just arbitrary, it has a specific magnitude. It is exactly equal to the weight of the fluid that the body displaces. So, if you imagine placing an object in water, the amount of water it pushes aside determines the buoyant force acting on it. And this force acts upward, right at the center of mass of the displaced fluid. This is a key point because it helps us understand why objects float or sink depending on their density relative to the fluid. This idea is neatly summarized in Archimedes' principle, which states that the buoyant force on an immersed object is equal to the weight of the displaced fluid. This principle is fundamental in fluid mechanics and helps us analyze many real-world situations, from ships floating on water to hot air balloons rising in the sky. By understanding this balance of forces, we can better grasp the behavior of objects in fluids and how they achieve equilibrium. So remember, the upward buoyant force is directly tied to the displaced fluid's weight, and it always acts at the center of that displaced volume. Let's now turn our attention to fluid mechanics. This is a fundamental area in engineering that deals with the behavior of fluids, which include liquids and gases. Understanding fluid mechanics is crucial because it impacts so many applications, from designing pipelines and aircraft to understanding weather patterns and even biomedical devices. In essence, fluid mechanics helps us analyze how fluids move and how they exert forces. This involves studying concepts like flow rate, pressure, and velocity, which are essential for designing efficient systems. Whether we're looking at how water flows through a pipe or how air moves over an airplane wing, the principles of fluid mechanics are at work. Throughout this presentation, you'll see how these concepts are interconnected with other engineering disciplines. Mastering fluid mechanics enables us to optimize performance, improve safety, and innovate in countless fields. So, as we proceed, keep in mind that understanding these core principles opens the door to solving real-world engineering challenges involving fluids. Let's now turn our attention to fluid mechanics. This is a fundamental area that helps us understand how fluids behave and interact with their surroundings. When we talk about fluids, we're referring to liquids and gases, which are both characterized by their ability to flow. In this section, we'll explore key concepts like fluid properties, such as density and viscosity, and how these influence fluid behavior. We'll also look into the principles governing fluid motion, like Bernoulli's equation and the conservation of mass. These ideas are crucial because they underpin many engineering applications, from designing pipelines to understanding aerodynamics. Understanding fluid mechanics is essential because it connects to many other parts of engineering. Whether we're working on mechanical systems, civil structures, or even environmental projects, knowing how fluids move and exert forces helps us make better, more efficient designs. So, as we proceed, keep in mind that mastering these concepts will give you a solid foundation for tackling complex real-world problems involving fluids. Now, let's delve into fluid mechanics. The unique properties of water and immersion have significant physiological implications when it comes to delivering therapeutic exercise. These properties, which include buoyancy, hydrostatic pressure, viscosity, and surface tension, all have a direct impact on how the body responds in an aquatic environment. Buoyancy, for example, helps reduce the weight and stress on joints and muscles, making movement easier and less painful. Hydrostatic pressure exerts an even force around the body when submerged, which can aid in reducing swelling and improving circulation. Viscosity, or the resistance of water to movement, provides gentle resistance that can be useful for strengthening muscles without overloading them. And surface tension, although more subtle, influences how water interacts with the skin and tissues at the surface. Understanding these properties is key to optimizing aquatic therapy, as they all work together to influence how we move, recover, and rehabilitate in water. They're fundamental to designing effective, safe, and targeted therapeutic interventions in the aquatic setting. All right, let's talk about buoyancy, which is a fundamental concept in fluid mechanics. Buoyancy is essentially the upward force that fluids exert on objects immersed in them. It works against gravity, meaning it can make objects seem lighter or even allow them to float. Now, a key principle that helps us understand buoyancy is Archimedes' principle. This states that when you immerse a body in a fluid, it experiences an upward thrust. The size of this thrust is equal to the volume of the fluid that the body displaces. This is really important because it explains why objects float or sink, depending on their density relative to the fluid. And it's a cornerstone concept that ties into many practical applications, from ship design to understanding natural phenomena. So, in essence, buoyancy is about the interplay between an object, the fluid it's in, and the displaced volume, all governed by Archimedes' principle. Let's talk about the clinical significance of buoyancy. As you can see, one of the key effects is that buoyancy provides the patient with a sense of relative weightlessness and helps unload the joints. This happens because buoyancy reduces the force of gravity acting on the body, making movement much easier. So, patients can perform active motions with less effort, which is especially beneficial during rehabilitation. Another important point is that buoyancy can be used as a resistance tool. When an extremity is moved against the force of buoyancy, it creates resistance. This resistance can be very useful for strengthening muscles, as it allows for controlled, low-impact resistance training within the water. Connecting this to fluid mechanics, understanding how buoyancy works helps us optimize therapy techniques. By manipulating buoyant forces, we can tailor interventions to individual patient needs, making movements safer and more effective. Overall, buoyancy is a powerful component in aquatic therapy, aiding both mobility and strength development. Let's talk about fluid mechanics and how it impacts buoyancy in the body. The amount of air in the lungs plays a significant role here. When the lungs are fully inflated, buoyancy increases because there's more air acting like a cushion, helping the body stay afloat. Conversely, if the lungs are deflated, buoyancy decreases, making the body less buoyant and more prone to sinking. Now, aside from lung air volume, body composition is also a key factor. For instance, obese patients tend to have increased buoyancy because fat tissue is less dense than other tissues. This means they naturally float more easily. Understanding these factors is crucial, especially when considering patient positioning and movement in medical or rehabilitation settings. Buoyancy isn't just about floating. It influences how the body behaves in water or other fluids, which ties into the overall theme of biomechanics and fluid interactions. Let's dive into the topic of fluid mechanics. Fluid mechanics is a fundamental branch of physics that deals with the behavior of fluids, which include liquids and gases. It's essential because it helps us understand how fluids move and interact with their surroundings. This understanding is crucial for designing everything from airplane wings to water pipelines. In essence, fluid mechanics covers the principles that govern flow, pressure, and forces within fluids. Whether it's the flow of blood in our bodies or the airflow over an aircraft, the concepts are similar. Throughout this section, I want you to focus on how these principles connect to real-world applications. Recognizing these connections not only makes the theory more tangible, but also highlights the importance of fluid mechanics in engineering and nature. So, as we go through this, keep in mind that mastering these concepts will help you analyze and solve complex problems involving fluids in various fields. Let's talk about fluid mechanics, starting with the concept of the surface of a fluid acting like a membrane under tension. This is what we call surface tension. Essentially, it's measured as force per unit length, which helps us understand how strong that surface membrane is. Now, the key property here is that the attraction between surface molecules runs parallel to the surface itself. This parallel attraction is what creates the surface tension. Think of it as a kind of invisible skin that resists external forces trying to break through. An important point to remember is that the resistive force of this surface tension isn't fixed. It changes proportionally to the size of the object moving through the fluid surface. So, the larger the object, the greater the force needed to overcome this tension. All of these ideas tie back to our overall theme of understanding how fluids behave under different forces. Surface tension plays a crucial role in phenomena like droplet formation, capillarity, and even the way insects can walk on water. It's a fundamental property that influences many fluid interactions. Welcome to Slide 15, where we focus on fluid mechanics. Fluid mechanics is a fundamental area in engineering that deals with the behavior of fluids, liquids, and gases when they are at rest or in motion. It's essential because many systems we design, from pipelines to aircraft, involve fluid flow. In this section, we'll explore key concepts such as the properties of fluids, including density and viscosity, which influence how fluids move and interact with their surroundings. Understanding these properties helps us predict flow behavior accurately. We'll also look at the different types of fluid flow, laminar versus turbulent, and why these distinctions matter for efficiency and safety. Laminar flows are smooth and orderly, while turbulent flows are chaotic and mixing. Recognizing these patterns is crucial in design and analysis. Throughout this presentation, you'll see how fluid mechanics connects to broader themes like energy transfer, system efficiency, and safety. By mastering these principles, we can optimize designs, reduce energy consumption, and solve complex engineering challenges involving fluids. Let's talk about the clinical significance of surface tension in fluid mechanics. When an extremity moves through the surface of the water, it actually has to do more work compared to if it were fully submerged underwater. This is because breaking through the surface requires overcoming the surface tension, which adds resistance. Additionally, when we use equipment at the water's surface, it also increases resistance. Essentially, both moving through and working at the surface can make tasks more challenging, which is important to consider during patient care or therapy involving water. Understanding these effects helps us better anticipate the effort required and optimize our techniques for effective treatment. This connection to surface tension really highlights how fundamental fluid mechanics principles influence real-world clinical practices. Let's take a closer look at fluid mechanics. This area is all about understanding how fluids, which include liquids and gases, behave and interact with their surroundings. It's a fundamental part of many engineering applications, from designing aircraft and ships to understanding blood flow in the body. One key point to remember is that fluid mechanics helps us analyze forces and flow patterns in fluids, whether they're at rest or moving. For example, when water flows through a pipe or air moves around an airplane wing, fluid mechanics allows us to predict how those fluids will behave. This field is also essential because it bridges the gap between theoretical physics and real-world engineering problems. It involves concepts like pressure, velocity, and viscosity, which all influence how fluids flow and how forces are transmitted through them. Throughout this presentation, we see how fluid mechanics connects to other topics like thermodynamics and structural analysis. Understanding these principles enables us to optimize designs, improve efficiency, and solve complex problems involving fluids in motion or at rest. So, as we move forward, keep in mind that fluid mechanics provides the tools to analyze and predict fluid behavior in countless practical situations, making it a cornerstone of engineering science. Now let's talk about hydrostatic pressure, which is a fundamental concept in fluid mechanics. Basically, it's the pressure that water exerts on objects that are submerged in it. Think about when you're underwater. Your body feels pressure from all directions, and that's what hydrostatic pressure is all about. This pressure isn't just random. It increases as the fluid's density goes up, meaning heavier fluids exert more pressure. It also increases with depth, so the deeper you go, the greater the pressure, like how the pressure on the bottom of a swimming pool is much higher than at the surface. Another key point is Pascal's law, which tells us something very important about how pressure behaves in fluids. It states that the pressure applied to an immersed object is transmitted equally in all directions. So, if you push on one part of a submerged object, that force is spread out evenly throughout the object. no matter which surface you push on. Understanding these principles helps us grasp how fluid pressure works in various applications, from engineering structures to natural phenomena. It's a cornerstone for analyzing how fluids support loads or how pressure distributes in different scenarios. Let's take a closer look at fluid mechanics. This is a fundamental area within engineering that deals with the behavior of liquids and gases in motion and at rest. It's interesting because it connects so many practical applications, from designing pipelines to understanding aerodynamics. The key points here are understanding how fluids flow, the forces involved, and how these forces impact structures and systems. For instance, concepts like pressure, velocity, and flow rate are essential to predicting how fluids behave under different conditions. One of the most important ideas is the conservation of mass and energy within fluid systems. These principles help us analyze and solve real-world problems, like reducing drag on vehicles or optimizing fluid delivery in industrial processes. By studying fluid mechanics, we gain insights that are directly applicable to many fields, whether it's mechanical, civil, or aerospace engineering, fueling innovation and efficiency. So, understanding these core concepts is crucial, as they underpin a lot of the engineering solutions that shape our daily lives. Let's talk about the clinical significance of hydrostatic pressure in fluid mechanics. When pressure increases, it can actually help reduce or limit effusion, which is the buildup of fluid in the lungs. This is especially important in managing conditions like pulmonary edema. Additionally, higher hydrostatic pressure assists venous return, meaning blood flows more effectively back to the heart, supporting circulation. It can also induce bradycardia, which is a slower heart rate, and helps centralize peripheral blood flow, directing blood toward the core of the body. Now, moving on to movement, water's buoyant force and hydrostatic pressure work together to slow down movements. This slowing effect is beneficial during therapy or rehabilitation because it reduces the load on joints and muscles, making movements safer and more manageable. Overall, understanding these effects helps us see how fluid mechanics principles are applied in clinical settings to support patient care and recovery. Let's talk about fluid mechanics and how they can benefit your recovery. First, hydrostatic pressure plays a significant role in reducing swelling. When pressure is applied, it helps move excess fluid out of the tissues, which can ease swelling and also promote better circulation throughout the body. This is especially helpful after injury or intense activity, as improved circulation aids in healing and recovery. Next, hydrostatic pressure can also relieve pain, particularly during exercise. It stimulates sensory receptors in the skin, which can decrease the sensation of pain. So, by understanding these fluid mechanics, we see how applying the right pressure can not only reduce swelling, but also make exercise more comfortable and less painful. These concepts tie into the overall theme of how proper techniques and interventions can enhance recovery and performance. Let's take a closer look at fluid mechanics. Fluid mechanics is a fundamental part of understanding how liquids and gases behave, especially when they are in motion or at rest. It covers the principles that explain how fluids flow, the forces involved, and how they interact with surfaces. This knowledge is essential across many engineering fields, from designing pipelines and hydraulic systems to aerodynamics and weather prediction. The key concepts include understanding pressure, velocity, and flow rate, and how these factors influence each other. For example, as fluid speeds up, pressure can decrease, which is a principle we see in various applications like airplane wings or venturi tubes. Fluid mechanics also involves studying different types of flow: laminar, where the flow is smooth and orderly, and turbulent, which is more chaotic. Recognizing these flow types helps us predict behavior and optimize designs. Overall, mastering fluid mechanics enables us to solve real-world problems involving fluids efficiently and safely, tying directly into the larger theme of engineering innovation and problem-solving. Let's talk about viscosity, which is a key concept in fluid mechanics. Viscosity is essentially the friction that occurs between the molecules of a liquid. This friction creates resistance to flow, meaning the more viscous a liquid is, the more it resists moving. Now, one important property to remember is that this resistance from viscosity is directly proportional to how fast the liquid is moving. So, as the velocity increases, the resistance also increases. This relationship plays a crucial role in understanding how fluids behave under different conditions, especially when designing systems involving fluid flow. Connecting this to the overall theme, understanding viscosity helps us predict how fluids will move and interact in various engineering applications. Whether we're designing pipelines, pumps, or analyzing natural phenomena, viscosity is a fundamental property that influences the efficiency and behavior of fluid systems. Let's talk about the clinical significance of fluid mechanics, particularly water. Water's viscosity plays a key role here because it creates resistance whenever you move actively through it. The shorter the lever arm you're working with, the more resistance you'll experience. So, if you're stabilizing an extremity proximally, that is, closer to the body's center, you'll notice that the patient has to do more work to move against that resistance. Conversely, stabilizing distally, or farther away from the center, reduces the amount of work required. Another important point is that increasing the surface area moving through the water also increases resistance. This is why larger or more exposed parts of the body face more opposition when moving in water. Overall, understanding these principles helps us design better aquatic therapy interventions by manipulating factors like leverage and surface area to control resistance. This knowledge is crucial for optimizing rehab and training outcomes. Let's take a closer look at fluid mechanics. Fluid mechanics is a fundamental area of study that deals with the behavior of fluids, which includes liquids and gases. It's essential because it helps us understand how fluids move and interact with their surroundings, which is critical in many engineering applications. At its core, fluid mechanics covers key concepts like flow dynamics, pressure, and velocity. These principles allow us to analyze everything from the flow of water in pipes to the flight of an airplane. One of the most important ideas here is the conservation of mass, which tells us that mass cannot be created or destroyed in a closed system. This principle underpins many fluid flow equations and helps us predict how fluids behave under different conditions. Another critical aspect is the conservation of energy, which explains how energy is transferred within a fluid system, affecting pressure and velocity. Understanding these energy transformations is vital for designing efficient systems like turbines or pumps. Throughout our presentation, we've seen how fluid mechanics ties into the overall theme of engineering and system design. It provides the tools and insights needed to optimize performance and ensure safety in various applications. By mastering these concepts, we can better predict and control fluid behavior, leading to innovative solutions across industries. Let's talk about fluid mechanics. This refers to the surface area of the body part that's exposed to the water when you're moving through it. The bigger the surface area facing the water, the more resistance you'll encounter. For example, if your hand moves with the palm facing into the resistance of the water, it requires more effort. But if you rotate your limb so that the ulnar border leads, you'll reduce the surface area exposed, and thus the resistance. Moving from a streamlined position to a non-streamlined position can actually be a useful way to strengthen your muscles progressively. By adjusting your body position, you can control the amount of resistance you face. Now, this ties into the overall idea of streamlining. Good streamlining minimizes resistance, making movement more efficient. But intentionally moving out of that streamlined position can help you build strength by increasing the resistance your body has to work against. So, understanding fluid mechanics and how surface area affects resistance is key to optimizing your technique and training effectively in the water. All right, let's talk about fluid mechanics and what happens when water molecules move. When the molecules are moving in the same direction and parallel to each other, That's what we call laminar flow. But as the flow rate increases, things start to change. The molecules don't stay in neat, parallel layers anymore. Instead, their movements become more chaotic and irregular. This transition is what we refer to as turbulence. When turbulence occurs, the flow pattern breaks down from smooth, orderly layers into a messy, unpredictable pattern of motion. It's a key concept because it affects everything from how pipes are designed to how air moves around aircraft. So, in essence, as the flow rate increases beyond a certain point, laminar flow transitions into turbulent flow, which is characterized by this chaotic, irregular movement of molecules. Understanding this shift helps us better grasp the complexities of fluid behavior in real-world applications. Let's talk about fluid mechanics for a moment. When turbulence is introduced, it creates an unstable environment. This instability actually encourages the core muscles of the body to work harder and become stronger. The goal here is to help maintain the correct position and posture despite the challenging conditions. Now, during this process, the patient is subjected to turbulence while standing, which adds an extra layer of difficulty. Maintaining your balance and position under these conditions requires significant effort and control. This kind of exercise can be quite advanced, but it's very effective because it pushes the body's stabilization systems to their limits. It's a great example of how challenging the environment can help strengthen core muscles, ultimately supporting better posture and balance in everyday activities. So, incorporating turbulence into training isn't just about adding difficulty. It's about actively engaging and strengthening the muscles that keep us upright and stable, even in unpredictable situations. Let's take a closer look at fluid mechanics. This is a fundamental area of study because it helps us understand how fluids behave and interact with their surroundings. Fluid mechanics is essential across many engineering disciplines, from designing pipelines to aerospace engineering. At its core, it involves analyzing the forces and motions of liquids and gases. One of the key points here is understanding how pressure, velocity, and flow rates are interconnected. These concepts are crucial because they influence how fluids move through systems and how efficiently they operate. Another important aspect is the distinction between laminar and turbulent flow. Laminar flow is smooth and orderly, while turbulent flow is chaotic and mixed. Recognizing these flow types helps us predict system behavior and design more effective solutions. Overall, fluid mechanics ties into our broader theme by providing the tools to optimize systems involving fluid movement, whether it's water supply, airflow, or fuel delivery. Mastering these principles enables us to create safer, more efficient, and sustainable engineering designs. Let's take a closer look at fluid mechanics. This is a fundamental area in engineering that deals with the behavior of liquids and gases at rest and in motion. Understanding fluid mechanics is essential because so many systems in our world, from pipelines and aircraft to natural water flows, depend on the principles it covers. Key concepts include how fluids move, the forces acting on them, and how they interact with their surroundings. For example, concepts like pressure, flow rate, and viscosity are central to predicting and controlling fluid behavior. By mastering these ideas, we can design more efficient systems, optimize performance, and solve complex problems involving fluids. Overall, fluid mechanics ties directly into the broader theme of understanding physical phenomena to innovate and improve engineering solutions. Now let's look at the definition of floating. A body floats in a fluid when its weight is exactly equal to the weight of the fluid it displaces. This means that when an object is floating, it's not sinking or rising. It's in a state of equilibrium. The key point here is the balance between the weight of the body and the weight of the displaced fluid. This concept is fundamental to understanding how objects behave in fluids. It also links directly to the law of flotation, which states that an object will float if the weight of the fluid displaced equals the weight of the object itself. Essentially, the law explains why some objects float while others sink, depending on their density and the fluid's density. So, in the broader context of our presentation, grasping this balance helps us understand buoyancy and design objects that can float or sink as needed. Remember, the core idea is that floating is all about this equilibrium between the body's weight and the fluid displaced. Now, let's talk about relative density. Essentially, it's a comparison between the density of an object and the density of water. We calculate it by dividing the density of the object by the density of water. This ratio helps us understand whether an object will float or sink. If the relative density is less than 1, that means the object is less dense than water, so it will float. Conversely, if the relative density is greater than 1, the object is denser than water and will sink. An important point to remember is that the lower the relative density, the easier it is for the object to float. This concept is crucial when we're analyzing buoyancy and designing objects to stay afloat or sink as needed. Overall, understanding relative density helps us predict an object's behavior in water, which ties into the broader theme of how materials interact with fluids. The average relative density of the human body is approximately 0.97. This means that, on average, our bodies are slightly less dense than water. The air in our lungs plays a significant role here, as it helps to reduce our overall density, making us even more buoyant. Since the relative density is less than 1, that's why humans have the ability to float in water naturally. Now, you might wonder, does body composition affect buoyancy? Absolutely. People with more body fat tend to float more easily because fat is less dense than muscle and other tissues. So, higher body fat generally increases our ability to stay afloat. And what about salt water? Adding salt to water increases its density, which in turn increases the buoyant force acting on us. That's why it's easier to float in salt water, like the ocean, compared to freshwater. All these points tie into the overall theme of understanding how our bodies interact with different fluids and the physics behind buoyancy. When an object floats in a fluid, it does so because the buoyant force acting on it is exactly equal to its weight. This balance point is what keeps the object suspended and not sinking or rising. Now, to predict whether an object will float or sink, we use a concept called relative density. It essentially compares the density of the object to the density of the fluid. If the relative density is less than 1, the object will float. If it's more than 1, it will sink. For example, our human bodies tend to float quite easily. That's because our overall density is lower than water, thanks to the air in our lungs and the composition of our tissues. The volume of air in our lungs increases our buoyancy, making it easier to stay afloat. So the key takeaway here is that floating depends on the balance of forces, buoyant force versus weight, and relative density gives us a handy way to predict whether an object, including the human body, will float or sink. Understanding these concepts ties back to the broader theme of how objects interact with fluids and why certain materials or bodies behave the way they do in water. Ships float because of the displacement of a large volume of water. Essentially, when a ship is placed in water, it pushes water out of the way, and as long as the weight of the displaced water equals the weight of the ship, it will stay afloat. This principle is called buoyancy. Ice floats because its relative density, or RD, is less than 1. That means ice is less dense than liquid water, so it naturally rises to the surface. This is why icebergs float in the ocean. It's all about the density difference. Wood also floats naturally because its density is lower than water. Historically, humans have observed and used this property for boats and rafts. Humans themselves tend to float because our bodies have a low relative density compared to water. Our body composition, including bones, muscles, and fat, allows us to stay buoyant with minimal effort. These examples illustrate the core idea. Whether it's ships, ice, wood, or humans, floating is all about the relative densities and how they compare to water. This ties back to the overall theme of understanding buoyancy and how different materials and objects behave in fluids. Today, we wrap up our presentation by highlighting the key references that support our discussion. First, we have fluid mechanics and hydraulic machines. by Dr. R.K. Bansal, which provides a comprehensive foundation on the principles of fluid mechanics, essential for understanding how fluids behave and how hydraulic systems operate. Next, we refer to Therapeutic Exercises, Foundations and Techniques, 7th edition, by Carolyn Kistner, a vital resource that guides us through effective therapeutic exercise techniques, emphasizing their importance in rehabilitation. These references serve as the backbone of our knowledge, connecting the fundamental science with practical applications in therapy and rehabilitation. They remind us of the importance of a solid scientific foundation when applying these concepts in real-world scenarios, ensuring our approaches are both effective and evidence-based. Thank you for your attention throughout this presentation.